Welcome back, everyone. I don't know if I can remove. Okay, that's better. So I'm going to. So this is the first talk I'm going to give. I'm going to give a very brief mini intro to reinforcement learning. So when Neil was talking on Monday, he already mentioned like 5 sentences about reinforcement learning. So this is not to teach the whole theory, all the algorithms and all of that. To think about which approach should I take. So these are the kind of things I want to focus on. The basic intuitions. How do you know if your problem can be solved by reinforcement learning? And what does that take? But if you're reading a blog post or a paper about reinforcement learning, there's certain terms, certain key things being used, like that it's good to be aware of, so that it's easier to get the general gist of what's going on. So let's start by first remembering what supervised and unsupervised machine learning does. Can somebody summarize the key things about supervised learning? So how do you know you can solve a problem using supervised learning if you have a task?
You have labeled data. Like you have a data set and the actual solution.
Is that enough, having labeled data? What are the properties of the data that you need to be able to use supervised learning? So there's something important about supervised learning. So this last sentence here, independent and identically distributed samples. Can somebody explain what that means? So this is something that people often assume when you're applying supervised learning, but it's almost a requirement. So the idea of this is that, let's think of an example where this condition is violated, and then if you're trying supervised learning, then basically the learning basically breaks down more or less. So if you have, for example, our greenhouse thing yesterday, we can collect data there. For example, every day you can collect temperature or pressure or something like that, and say you wanted to, then they say we even have additional things. For example, somebody asked about if we can control something. So if say we were able to send a signal to turn on the heat, for example. So if every time we send something, it turns on the heat, and by turning the heat, we change the temperature. So there's a correlation between those two things, those two variables. So then if you're going to collect samples from that and then do something with it, you have to be careful that they're not correlated in some sense. So that's what this IID sample thing does. And this table I just summarized. So supervised learning, like somebody says, you have labels. Generalization is simply what you're testing is, after all your training, everything, how well do you perform given your samples. The same thing more or less work for unsupervised learning, except you don't have labels. So in unsupervised learning, you look at just the samples and you try to see some commonalities between them. For example, if you're clustering, you can think of, if they're images, you can try to see colors or something about orientation. So you try to see something that is you're able to take a huge pile of data and then break it into commonalities. And you can do the inverse of that, so that if you already have those commonalities and then you're given something new, you can try to see if it doesn't match in any of your clusters already. So either it could be an anomaly or something like that. So what I'm saying here is that anomaly detection and supervised learning are very tightly related. So any question on this summary first before we go to RF? Okay. So let's go to RL now. So reinforcement learning is paradigm just like supervised learning and unsupervised learning for which has a few characteristics. So the key thing that you want to look out for, there's a notion of interaction, there's a notion of sequences, and then there's a notion of this delayed consequences, which I'm going to go into quite well. So just a session before, we talked about the idea that almost everything in the real world has some sort of time dependence, which means almost every important data that you have out there has some temporal aspect to it, some sequence nature to it. So most reinforcement learning algorithms require at least that only applicable when you have a domain where there's that sequence nature thing. So something happens, and then something happens again, then something happens again, and things continue like that. The key thing you want to, key aspects you want us to sort of go into is what are the players. So in supervised learning, you just have your data, then you have your model, which you train, and then you have your new samples, and then you predict on that. So in reinforcement learning, you have these two key blocks, which we want to go into deeply. So there's a notion of an environment, just like our greenhouse yesterday. So you have the greenhouse is the environment. So it's the world of, you want to do something. Let's say you want to optimize for ripeness of something. I don't know, you're growing tomatoes or something in there. And your goal is that after 3 months, you want to make sure your yield reaches some goal. And so every day you measure some things, and then you have a choice of tweaking something. I can turn off the heat or reduce the humidity or something, and you do these things, and then they affect the quality on a day-to-day basis, and this continues, and at some point you reach some goal. So the agent in this case, so this is the program in reinforcement learning. So the agent is the mechanism which we use. Every time the agent can do something, in our greenhouse, you can write a program which to all of those readings, the pressure, humidity, and then it decides if you wanted to attain the goal of ripeness in 3 months, maybe you should turn the heat a little bit based on some knowledge. And the environment response, where respond here means that so when you turn the heat, your sensors which you're using, which are the things you use to observe or see what's happening there, you're able to observe some change. So you're able to observe that now the temperature increased or did it decrease or something like that. So that response generates a new state of the environment. So if you can think of if you can summarize the whole state of the environment as being, for example, what's the current temperature, what's the current humidity, what's the current pressure, so that is the state. So every time you do something, take an action, that state changes, so you're in a new state. And in this new state, you can again take another action, and then something changes again. Additionally, in reinforcement learning, we have this concept of a reward or cost in some fields like economics. So because we are trying to reach some goal, so you can think of, for example, in our greenhouse, you can think maybe you have another additional sensor like, I don't know, camera, which is looking at your fruits. And the camera has some sort of algorithm to determine, let's say, ripeness or something. So you can say, you do something and then some quality of the fruit changes. So that this could be a good or bad thing, so this could be the reward. So you're trying to see, you do something and you improved some aspect of the environment. We're going to go much deeper into how do you come up with these things, how do you design something like this, and all of that. Yes?
So why in that diagram, why do you have the state t+1 and then the state t?
Oh yeah, that's a very good question. So this diagram, so what happens? So this line, so there's the current time t. This is where we are. So at this current time, the agent with these sensors observation, it's looking around. It's at the current state is t. So based on what you can see, you can summarize that this is the current state. And now you also you get a notion of reward. So this is our payoff now. Then the agent takes an action now at the current time. And then after that action, the environment responds with a new state and the reward in the next step. So That's how the whole thing plays. It starts here, and then you go like this. Everybody understand that? So this is just, don't worry about the equations. This is just so that if you're reading a blog post or the environment is that world in which your agent lives in, and this can be very abstract. So I'm talking about greenhouse, but it could be a robot living in a room. It could be an autonomous car, in which case the world would be the road or the scene, for example. And this environment determines, for example, what choice of actions you can take. So in the greenhouse, the choice of actions could be turning up a few knobs. In a self-driving case, because the world is a road, so actions could be turn left, turn right, I don't know, stop, something like that. And then the state is just how you describe that environment at any given point in time. And there's a key distinction here to make. So observation and the state. So observation is just, you can have sensors and just one of them gives an observation, but that doesn't mean that it's a full state. So the full state is collect all of the observations, and that is the state. And so the state can be, so S1 here means this state 1, which can be a vector, a matrix, or whatever. It could be an image. So this is very abstract in that sense. And then action here again can be something high level as turn up something, something down, or it could be something fine grained, like in a car example, it could be turn the steering wheel 2 degrees. That could be the action. Or step on the brake 20%. Yes?
In the self-driving example, incidentally, how big are the state and action spaces in two-dimensional?
It's a very good question. So because you as the data scientist, you are the one doing the modeling, you have some sort of freedom in determining this. I mean, the problem kind of dictates it, but you can decide to make these things discrete. So for example, in the greenhouse case, you can decide to say that if the only thing you could control was temperature, you can decide to say the only thing you can do is turn it 10 degrees up or turn it 10 degrees down. Or you can decide to say turn it 2, 3, 4, and so. And that choice determines how many possible actions you can take. So it can be very small, discrete set, or it can be basically continuous and infinite. And that choice has serious consequences down the line in terms of what algorithm you can apply. Because as this state space and action space grow, the choice of algorithms you can use also change in terms of how much computational requirements they need and all that kind of stuff. So this is what I'm summarizing here. So one other thing to point out here is that we are going to make this very clear. So remember how the interaction works. So at any given point in time, your agent is observing the state, looks at the things it can do, and then picks one of those things it can do, does it, the environment responds, and just keeps doing this. And you can imagine every time the environment responds with a reward, you can store it. And so the in reinforcement learning, the goal really of your agent is to maximize these returns. So the return is just, now I got the return of 2, whatever 2 means. Then next time I got 1.5, and I can just keep accumulating this. Almost like, if you think of like stock market. If you had an agent where you give it access to your pool of money, and then every day it has a choice of invest in company A, B, C, and D, and then it makes the choice, then the stock market, which is the environment, responds by either it loses $2 or against $3. And the idea is that over a period of time, you want it to maximize these returns. And now the whole challenge in reinforcement learning is how can we develop algorithms so that which allow such an agent to do this automatically, so that you just set it free, and then over time you basically generate this rewards. Yes?
I think in whose perspective, on an abstract level, in whose perspective is the reward?
Sorry?
In whose perspective is the reward? Is it for the agent in that environment, or for the
Designer?
the benefit of the human being?
So this is very key. So that's a very good question. So the question is, the reward is with which perspective? Is it with the perspective of the agent or of you, the data scientist who is designing all of these things? So the idea is, you as a data scientist, the agent is the same way in supervised learning. The agent corresponds to more or less this model. It's your window into this world. So you decide these parameters, then the agent collects the reward. So your job is to tell the agent to do something that matches your motivations. So this is a problem called value alignment. So the agent should be doing something that is aligned with your own value system. Like in terms of investment case, you want to increase your returns. So you design this thing in a way that the agent's core purpose, everything it does is doing so that it aligns with something that maximizes something for you. And obviously, maybe not obviously, but you can imagine ways in which there can be friction between those two things. That bandwidth of expressing your desires into this agent world is not, there's information loss in that sort of communication channel. And when that happens, you end up with an agent that does something which is correct according to the framework, but it doesn't meet what you need. And this usually happens, for example, when you don't properly design your reward function. And we'll go into how do you design a reward function. Before we go further, so I said we take an action, the environment responds. So how does the environment generate this new state? So like in our greenhouse case, so you turn on the temperature, and then after some time the temperature increases. But what process causes that? So there's some laws governing that. In the greenhouse case, there's physics or thermodynamics, or there's something that says, if somebody turns the heat there, then that all the thing disperses, and then so that the sensor on this other wall will pick up the new value of temperature. So there's a function, there's a mapping which takes that action you take and then get again a bit this. So this is what is called a transition function. So it's the thing that governs how does the environment move from one state to the next, and it's conditioned on the action you've just taken. Yes?
Yeah, just follow up on that. So is the transition state, the function, is it time sensitive in terms of step 1, step 2 discretely, or is it considered continuous?
That's an excellent question. So I'm defining it here very abstractly. So this thing can be something that is probabilistic, it can be deterministic, or it can be dependent on time, all of those things. So for example, in a self-driving case, if the action was turn the steering wheel left, then the transition function there is the physics of what happens once you send the voltage to the steering wheel and then the wheel starts turning. So all of that summarized in transition. And the steps could be when you made that decision and when it ends up there, so those could be discrete, or the steps could be really at every point in time as it keeps turning. So this thing could be as complex as you need. So you can model this thing using neural networks or whatever you want. So it's just, you can think of it as just a box. You send in an action and out comes something else. And the time block for which that happens can be a long span of time, or it can be 1 second or 10 seconds. So this is a design choice. You can also think of it in economics like you're a municipality or city council. In that case also, let's say your environment is, I don't know, the school system. So you make an action to fund the school system. And then over a period of time, something happens, and then you end up in the new state of your school system. Are people doing better or something? So that is then the transition in that case. So this time step here could be years sometimes. So it depends on the context of the problem you're modeling. I should keep. And then the reward function is very closely related to the transition function. I'm using F1 and F2 here just to emphasize the fact that these things are just some function of something that comes in. So it's an input that comes in, something goes out. The reward is, again, so both of these things are things that will live in the environment. So the environment influences the choice of these things. And in this case, because this is the environment, you do something, environment tells you thumbs up, thumbs down, or thumbs up by 2 degrees or by 10 degrees or something like that. So that's what this is. It's some notion of, like in the stock market case, you go crazy one day just investing randomly, the stock market punishes you heavily by telling you no, you lost $100 or something. The next day you be more careful, you only lose $2. So that is this function. And like I said, the overarching goal is you want your agent, as it continues interacting with this environment, to maximize those returns. One side note here, just so that if you're reading a blog post or a paper, in other fields, more engineering sides like robotics or control, people usually talk of reward as a cost, and nothing changes. Because you can think of one of these things as just the negative of the other one. So if you invest and then you get a reward of -1, you can also think of that as a cost, and then the framework works either way. Any question? Yes.
Going back to a point mentioned on Monday.
Yes.
Now that I see this looks exactly like a control loop.
Yes.
How is it different? How is it worse or better?
That's a very good insight. So reinforcement learning is very much related to control. I'm going to emphasize this a bit. So people in control know about, in control engineering, you have this notion of direct methods and indirect methods. A direct method tries to generate control laws without doing system identification. So those ones will correspond to a class of algorithms here. And indirect methods will also correspond to a different class of algorithms here. And I'll get that point very clear. So they're very related. In fact, the underlying theory is more or less developed in sync. So these ideas, then control, then economics, then game theory, they're very related all the way to mechanical design. Yes.
Would you explain that again, like the difference between the process control and reinforcement?
So sometimes there's almost no difference. So the thing is that, so there's a part of control called optimal control. So, and there's a part of that called direct adaptive optimal control. So that corresponds exactly to model-free reinforcement learning. So where the only thing that changes is just control people would call something a policy, and here would call it something else. So this is kind of a summary of comparing the three things. So one key thing to note here is, remember this, our IID thing. So in supervised and unsupervised learning, we had some X, and then there's some Y, or just X and no Y in a supervised learning case. And here now we have some state, some action, then outcomes, a new state, and some reward. So this is your data in that sense. So if you had to collect a data set, this is what the data set basically contains. Like, so this could be out of 4 things, and then you can have a whole pile of those. So that is the data. And now it's important to see here that the data, the next data, so if you have one sample, so this is sample X, then the next sample X1, the X1 sample is related to this one, because there's a connection between this current state and the previous state through these 2 functions, the transition one and the reward. So this breaks that IID assumption. Second thing to note, is that clear before? So the next thing, so there's this concept of delayed rewards, which we're going to get into. So the idea is, so you do something now, you get a reward now, and then the next time step again, then you can follow that path. So reward 1, 2, 3, up to, I don't know, 1,000. So there's a way in which the reward you get at time 1,000 somewhat influences what you do now because of this connection with these functions. And we'll make that clear very, very soon. Now, this thing of the next state depends on the previous one, this in the theory is summarized by something called a Markov property, which means what I do now depends only, what I do next only depends on what I do now, but not the past. So the past is completely summarized by the present, and then the present determines the immediate next future, and then again, we forget all that past, we summarize again, then we keep going.
Question.
Yes?
Are there any practical applications where you actually need more than just the first order Markov assumption?
Yes, so that's a very good question. So sometimes the fact that we only have now and then immediately, sometimes this breaks down depending on how you model these things. So imagine, sometimes you want this one to depend on this st and also st minus 1 and maybe st minus 2. You want to depend on like a small bit of history. And the framework allows you to do something like that. Then we call them semi-Markov. In practice, so for example, I guess a good example is like in the self-driving car case, depending on how you model the choice of actions, for example, if you want to do a lane change, it depends a lot on there's a lot of history involved that influences before you can make that lane change. If you have just made a lane change before, the likelihood of making another one is much lower than if you're already keeping lane. So therefore, having that history helps. But the key point is that the framework which is underlying all of this, the math, the theory of it, allows you to still express that very succinctly. Yes?
Just a point of interest, does the field also allow you to model consequence and sort of retrospectively model like the reward?
Yes, so the consequence is embedded here. So the reward here is a positive looking thing, so people like that, but you can just think of this as cost. Right? So especially in robotics, people think as cost, like you're trying to get somewhere, you want to avoid, I don't know, puddles or pools or something, and you can say every time you enter a pool, there's a penalty, the cost of minus, I don't know, 1,000 or something. And then in that case, the goal is to minimize the total cost as you keep traversing instead of maximizing the reward. Yes?
What is the difference between the reward and the new state? Because since the outside was the same input, maybe the function difference is there.
So-
Apply on those inputs. For the first state, there is the ST in action.
Uh-huh.
There is the current state in action, and then in the reward, there is current state in action. So what makes the results different?
So the difference is really in these two F's here. So the F here, so this, the thing that takes this thing and produces this is dramatically different from the other one. So in this case, this could be the laws of physics, which, if I try to jump, I'm going to end up in a new state, and that new state is completely determined by the laws of physics of this planet. But if I'm, for example, if this place was on fire, and then I jump into that place, the reward is determined by the fact that I move from a place with no fire to now a place with fire. So you see, that's how those two functions are different. They're all taking the same thing, so I still move from the same place or the same action, but where I ended up is governed by a different set of laws, and also the penalty, the reward is a different function. Is it clear? Okay. So it's just a few more key concepts, and then we dive into a practical example with the solar panels. So if you remember our loop, this interaction thing. So you can imagine this keeps going on and on and on. So the question is, let me go here. So there's two things to distinguish here. So there's certain tasks, for example, like in the stock market. You put your agent in today and you want it to go for 3 months. And then at the end of the 3 months, you want it to have maximized. And then you say, maybe after 3 months, you say, that's it, I'm done. Stop there. So, or, for example, you're doing something in which there's no clear end in sight. It just wants it to keep running and running until infinity. So that's the separation of these two things. So there's certain tasks which you can break it into segments. So if you want to use this into games environment. So in a game, you start playing, then at some point somebody wins or loses, for example. And at that point, that's the end of basically that universe, right? So then you can restart the game and then play another round. Then start again, then play another round. So those kind of tasks, they're episodic, and the episode is one run through that. So if your agent was learning to win games, for example, that's the goal. So it will play one round, At the end of it, it knows if it won or didn't win, and maybe it collected some, maybe it won, it lost by, I don't know. It came very close to winning but didn't win, so it can record that, play again, record another one, and then do this over and over. And with time, all of that history should be able to help it at some point it will win. Here in this, in continual tasks, there's no clear notion of when something ends, so it just keeps going. So these tasks, for example, in industrial control, for example, you could have a machine that, I don't know, makes something and it has some parameters and you're controlling those with an reinforcement learning agent. And at any given point, the agent is making actions to optimize something, maybe output of the process. And this just keeps going as long as the machine keeps running. There's no clear notion of when it ends. Or in a more futuristic example, you have a robot at home who's your butler, and the idea is that it does things for you, and occasionally it does bad things, sometimes it does good things. And ideally then it should just keep improving until one day you destroy it. Right? There's no clear notion. There's no notion of it goes at some point and then you reset it. I mean, unless you buy a new one, then that's kind of like a reset. Any question here? So one last thing here is that this is just terminology. So as this protocol continues, so you go to some state, you do something, then keep going. So you can collect these things. You can say, I was here, did something, ended up here, did something, and you can collect that, because remember, you can do that but still not go at all the possible states. For example, if the states were these squares here, so I can keep jumping until I reach the door, for example, then I will have traced a path. So that we call a trajectory, or some people call them rollouts or something like that. But this is important. This is going to become important very soon. So now, given any such trajectory, you can have your agent try to do something, like just basically follow through, especially in episodic tasks. Just follow through, like play the game, play until the end, record all of that, and it can record how much did you get. So what is the return of that? If we could, for example, if the game was chess, it could just dumbly just keep doing, putting the pawn ahead and all that stuff, and then go until the end and then record that. And then the next time maybe tries using the bishop or something like that, and then record all that. So that is summarized with the notion of, that's how you get this idea of a return. So return is just sum them up all to the end. And there's an important thing about that. So think about the investing case. You have your agent investing in the stock market, and let's say you want to run it for, 10 years. So if it wins you, $2 today, and if it wins you $2 next year, are those $2 worth the same to you? Why are they not worth the same? Or people in economics, the idea of inflation. Can somebody explain us briefly the idea of inflation? What is inflation?
The time value of money decreases.
Sorry?
The value of money
Decreases over time. But why does it decrease? So, I mean, the quantity of money is still the same, but the value you assign to it decreases, right? Yeah. So in our case, our agent, again, like, this interaction could go on for a very long time, and you want the agent also to have some idea that things really, really fine in the future, the values are less than what is now. So this is what we do with the idea of discounting, that the returns you get now are worth more to us than what you get much further in the future. And we do this, don't worry too much about the math. This is just so that if you see it in the equation, it's not strange. You do this using this parameter, so that you can set this to some, 0.9, and then you can imagine the one at the 10th step will be worth much less than this. So therefore, if the agent is optimizing, it's also encouraged to get you also some short-term things without losing sight of the overall goal. Yes?
So that
sometimes you'll have to go a particular route that at that moment in time might not seem ideal, but you get to the destination closer. So wouldn't that be perceived as the future reward is better than the current reward? So how does that come into play with that?
That's a very good question. So the question is, in certain examples, like in self-driving cars, for example, like routing, basically, it may appear that sometimes you want to do something less optimal. You take a route that maybe is not exactly heading you where you want to go, but in the long term, it's helping you to get there.
Yeah.
But that is a key thing. The idea is that this thing that you do that someone looks like is not the ideal thing to do, it's helping you something. And that help is more valuable to you now than the other way around.
Okay.
So there's a very famous experiment.
That would still be considered a current reward, even though it seems objectively at the time as a deterrent.
Yeah. Yes.
So does this mean that the agent will have to do a prediction of future states and future rewards it would get to do this computation?
No, the agent doesn't do any prediction. It's just it takes an action, and then the environment tells it this is what you get. The agent that does it. I mean, it can build a model to try to predict, and we'll get to that because then it's doing planning in that case. But the classical thing is the agent it only encounters the rewards after it has received them.
So how would it know what the reward it will get in the future and do that prioritization?
So that's the thing. So when it's here, it doesn't know anything about this. And when it's here, it knows that it has received this, and this was worth a lot more, and this one is worth less in that case. You see, so it's experiencing this thing one step at a time, but it can keep a record of what has happened in the past. So there was a very, I would say, like messed up experiment with this way back at Stanford, where somebody put children in a room and then offered them one marshmallow and then told them if they like, they could not eat the marshmallow and wait for another half an hour, and then they'll get a second one. And the question, the idea was how many of the children would resist the temptation to just eat the one they already have or wait for the next one. Is the second one as valuable as the first one? So some children did wait, but the temptation to devour this one was very high, very, very, very. The temptation just is greater and greater because some people also say it with I don't know. When you're really thirsty or something, then you go to the first cup of water you drink. It's much more valuable than the second one. Okay, so 2 more things and then we go to the example. So all this time we've been talking about the agent is at some state and then takes an action, but how does it know what action to take? How does it decide I'm going to turn left or turn right? So the thing that governs that is something we call a policy. A policy is it's a prescription basically. So the agent, imagine you as the data scientist, you can give the agent a policy. You tell it, every time you see this, do this. Every time you see this, do this. So you give it it's almost like a table. I mean, if the number of states is small. If the number of states is small, you can just list, you're in state 1, do this. State 2, do this. So, and the way I'm describing it is the deterministic way. So there's only one thing you can do. But sometimes you can tell it, if you're in this state, try and do this thing because maybe there are more inputs with this. So there's a probability of the possible things you can do. So then in that case, it's stochastic. So it can be a simple table, like I say, or this can also be another function. You can imagine you can have a very complex function where every time the agent is in a new state, then all it does is it says, now I'm here, this is the state, send this into the policy function. The policy function responds and telling it, okay, this is the recommended thing to do, then it does it, and then continues like that. So naturally, you can imagine there are better policies, there are bad policies, there are good, all of that. There's a whole spectrum of policies, right? So for example, if my goal is to go to the door, maybe you have a policy which says, just keep moving like this. Or another policy could be always walk one leg like this. And then there's so there's a whole spectrum of policies. And in reinforcement learning, the idea is that you want your agent to learn the best policy, because with the best policy, for example, in an investment case, the best policy should give you the best returns, which is the overall goal you're trying to get into here. And that's what is summarized here. This is the reinforcement learning problem. The rest of what I just said before was just modeling. It's just making a choice of what is a state, what's an action, what's a reward. Yes?
I had a question about the policy.
Yes?
So, with just using an analogy with control, is policy more so the method you use to get to the end, or is it rather the feedback to ensure that it gets to the end? So, for example, if your system is deviating from the goal, is it that function to sort of bring it back towards the goal, or is it the method through which you get to the goal? If that makes sense.
It is a function to bring it back.
Bring it back.
Bring it back. So the policy is the thing that would be able to correct you or encourage you. So it's it's really a prescription in that sense. Yes.
I was thinking the scenario of the chess game.
Uh-huh.
Does a reward come after every move or the final move?
That's a very good question. So the question is, if we're talking about a chess, that's the environment, should the reward only come at the end when you win or lose, or should it come after every move? And that's a choice you make when modeling, and there's consequences of that. So a lot of papers published today from DeepMind or whatever, people model the reward only at the end. And so giving the reward after every move means that by the time your agent, even if your agent doesn't win, it still gains information. It still knows that I almost won. So that is still useful. But if you're only giving it win or lose, if it comes, I don't know, 99% to winning but doesn't win, it doesn't know that I almost won. It's almost like that policy was just useless. So it will have to try again, because the idea is that if you already have a policy that almost gets you there, maybe next time you just start from there and then correct a few things.
Okay, in that same scenario where how good my move is depends on what my opponent plays at times. So when I make a move like a sacrifice, hoping to gain something for that sacrifice, using that piece will it count as a loss at that point? Knowing that I'm doing it to get something, but at times you play and you want to take a piece out of the way to checkmate or something. So would that loss count as a loss? Would that count as a loss or just count?
Yeah, so that's again a modeling question. So you can have a reward which every time you lose a piece, you get a drastic, like a huge negative. And the idea is that it should be okay that if you get a few negatives and mostly positive, that should still be fine. So the framework should allow this. Okay, this is the last thing, and then we go to the. So I said there's policies, right? And I already mentioned the idea that there's better policies. So some policies are better than others, but how can you make that concrete? How can you, given two policies, I give you policy A and policy, how can you tell which one of them is better? And how you do that, you're using this idea of something called a value function. The value function says, in that environment, you have all your states. I can go in all of the states, I can take one policy, right? And then using that policy, go over all the states, do what the policy says. So if I'm state S, go to S, do what the policy says until the end, then I collect the return and then store it. Go to another state, do what the policy says. And the idea is that if this policy is better than this policy, then these returns that you collect from this policy should always be greater than these returns, meaning the value over all the states of the better policy will always be higher than the value over all the states if you use the other worse policy. Is that clear? This is just I just put this here because if you try to read a paper or a blog post, there's so many notations. So what I'm putting here is more or less the standard one from the main book, but you don't have to worry too much about it. Yes?
So is this the part that really defines the idea of reinforcement?
Exactly. Yeah. Or you alluded to something more?
No, just, yeah, I just wanted to ask, what part really represents the ethos of reinforcing?
So the reinforcing part is like, remember, you do something, the environment responds, and that response is somewhat part of that reinforcement, right? Because that response, that feedback then influences something that you do. I'll get to the connection to animal, like biological system where the enforcement thing comes to. Okay, so let's see. I'm going to quickly go over this because how much time do I have? Okay. All right. So once we set up all of those things, so this is what I just said. If you want to know if one policy is better than the other, you compute this value thing. Basically, you take the one policy, you go over the all states, compute those values, those returns. So in your stock market case, you have policy A and B. You can take policy A, invest for 3 months, for example, and then policy B, invest. And then if policy B is really better, then you always have higher returns than policy A. And then there's two things here. So remember, all of this thing is called reinforcement learning, but where is the learning part? So the learning part, so there's two things. If, when modeling, if somebody already gives you access to the reward, the state, the action, the transition, all of the reward, if somebody gives you all of that, then your job is really just to plan. Your job is really just to try and find the optimal policy, and once you find it, then just use it. You're done. You don't need to do anything more. So the learning really in enforcement learning is when things get interesting, when one of those things is not given. For example, you don't know exactly what the transition function does, or you don't know exactly what usually that's most the common case. For example, like in, like for example in a self-driving car case. So you know that you can take a few actions, but where you end up, you know something is guiding that process, but you don't know exactly how it's guiding that process. You do not have the complete idea of that. So you could try to learn that transition function itself, but because as you keep experiencing, as you keep going through that world, every time you do something, something happens, you can keep the record, and this forms a data set, right? And then you can fit a model to this. You can also learn a policy. So there's methods which, even if you're missing some pieces of this, they can sidestep the modeling part and then directly try to optimize the policy, and we're going to use one of those today. And you can also learn the value function, basically, because remember the value is any point in this world, the value is what is the expected return from there if I follow some policy. And you can also learn that by just experiencing, just keep going on over, I don't know, a million times, and then use statistics to average things. So onto the algorithms for doing this, there's somewhat a taxonomy, a family of algorithms. We won't go deeply into this. I'll just explain the key distinctions. So the main distinction really is this model-based things and then there's model-free things. So this is where then the connection to control becomes also more clear. So model-based means you already have everything. You have the transition function, the reward function, all of that. So now with all of that, your job is to just find the optimum policy. So there's algorithms in that class. If you've been following the news, some of the more popular algorithms in that class, which are recent, for example, the AlphaZero algorithm that DeepMind used to solve the game of Go, that is a model-based algorithm that falls here. So it's already given the model. And then there are some which learn the model on the fly. So a popular algorithm there is something called world models. I think it's from DeepMind. So that's in this class. And then there's those which just keep learning the model all day. They just go straight and trying to find a policy. Q-learning is, I guess, one of the most popular algorithms out there. is false here, and then there's some which it's a class called policy optimization, where the idea is, like you said, the policy is a function which tells us something, which means just like any other function in machine learning, we can decide to say it's a polynomial or a neural network. You can choose some parametric form and then try to fit something like that. So these things, the optimization is optimizing, for example, weight of some polynomial so that the resulting policy is the correct one, or it could be optimizing weights of a neural network, so that that neural network is the policy. Any question? Okay. So I'm going to go straight into the example we have, and then I'll come back to this. So yesterday, when we were doing the greenhouse thing, I think everyone remembers we had to use a generator to power the gateway. So, somebody proposed a solution. Why don't we just put the gateway somewhere in the middle of nowhere and then put solar panel in it, and then we have power. And in that sense, we don't have to use a generator. So close to the equator, most of the time you just stick a panel up is good enough, because the sun is more or less always up in direct incidence rays. But other parts of the world, for example, if you're in the south, like South Africa, sometimes the sun is all the way in the north. Different periods of the year, the intensity of the sun varies. So imagine if you could have a mechanism to tilt the panel, to orient it to face the sun more, because the idea is that the output of the solar panel is really directly affected by how much the angle of incidence. There's a way in which you can inject domain knowledge in the one. So this is not new. This is something I took from physics. So physics already tells us that the output of that thing directly is influenced by these three things, among other things. So there's something called irradiance, which is directly affected by, I think I can draw here, or maybe, let me show you this example. So if this was the panel, and that's the sun, the rays come from the sun, the angle in which they hit the sun affects how much energy you can get out of this thing. So imagine if you can have an algorithm, like an agent in this case, which somehow tracks where the sun is and a few other things, and then takes an action where the action would be move the panel a little bit. And the goal, of course, is over a period of time you want to get the most energy out of this thing. So this is the problem we want to model. So going back, so this is a typical prototype how you could do this actually in the real world. So like you could have, this is our panel, you could put a simple mechanism like basic motor, and then put something here, connect it to some kind of Arduino or one of the boards we had yesterday. And then you can turn some motors. So for example, you can actuate this, or you can rotate something. So as a scientist, you make the choice of how many. Do you just want to turn it in one axis? Do you want to turn it in two axes? And there's consequences to that. So this is a modeling thing you make. And now, given that, we can now use reinforcement learning to try and optimize for maximum energy output. So how do we do this? So now that you know the problem, a quick question is this something that is episodic or a continual task? Episodic, why is it episodic? So? Because the? So he's saying it's episodic because the sun shines for at most 12 hours. So
I would think it was continual, because it would be constantly seeking the sun, irrespective of whether it was shining or not.
Let's say we do east, west, and north, south. So we do 4.
Well, it's east, west, and it will be
So this is just to, this is the transition, the physics of it. The idea is that the things we need to track is this angle and this angle. So this is something that, domain knowledge we read from physics. What about actions? So what are our actions in this case? How do you model the actions? So we said we are going to do east, west, and north, south tilt. So, but how? So, what would be? How would you model that? Do you want to tilt by 0.2 degrees, or you want to tilt by 10 degrees every time you make it, or? And how often do you want to tilt it? Any ideas?
I propose that it will be dependent on how much resource you have.
Which resource? Which resource?
Say how much energy you collect, or how much energy you spend. So that would be the cost on moving and tilting.
So
Depending how much you collect. So yeah, do you want to tilt every hour, or if you have constant supply every second?
So that's a very good point he brings. The idea that to tilt the panel costs work. It is not free to tilt the panel. So we get energy from this thing, store it, and we're going to use some of it to tilt it. And that the part we've used, we have to subtract it. Because remember, in the grand scheme of things, we want to maximize the total energy we can use for other things, not for tilting this thing. So that means the choice of how much you tilt and how often you tilt is also a parameter which you have to take into account here. So there's a trade-off there. You can just go tilting the thing all the time, because then you may end up properly tilting it and actually generating a lot of energy, but then using all of it. Because the baseline, so the thing you're competing with here is, what if you didn't do anything? You just put it there. The idea is that the hope is that we should be able to generate more energy if by tilting it after you subtract the cost of that tilt. So just to rush to this, so this is not something new. So people have tried to do this and publish papers, and so the ideas I'm going to present here are from this paper. So these are the action sets they use. So you can do nothing. So at some point the thing is facing some direction. So if the time to take an action comes, you can decide, I'm just going to do nothing, don't do anything, just leave it. Or you could tilt it in any of these directions, and in this case they're doing it by 2 degrees. So these are the actions. And then the state So the state in this case is where you are, so where the solar panel is, right? And where the sun is, so the angle of the sun's rays, where how it's coming, because those two things affect the irradiances. And then there's one more thing, which so the sun will be directly here, and you're nicely tilted, but the cloud cover is, blocking everything. So in such a way that it may be best to slightly shift the panel a bit so that you catch some rays which are going somewhere away from the clouds. And reward, like I say, it's just the total energy. The reward is energy generated at any given point in time, and then the goal is to maximize that sum of the period of time. So you could say every day I want to make sure I get the maximum amount of energy from this panel. All right. So in the notebook I gave, I put links to, so there's, people have simulated this, so you can generate, because you know where the sun is and you know where the earth is. From physics, we can compute this test, we can simulate this whole thing. We can also simulate clouds. In this case, we generate basically images of the sky. So the idea is that you can simulate a world in which you put a camera on the panel, and the camera looks up, and the camera can take a picture, and then that picture tells you something about the cloud cover. So we can simulate this as well. In this case, we simulate it using Gaussian, basically multivariate Gaussian. And then, because now we have a simulation of the whole thing, so we can generate state, do something, generate a new state, because we are simulating the whole thing, and then run it for a couple of times, and then see if this is actually worth doing. So the algorithm we are going to use is Q-learning. I won't go into details, but this is the core intuition of Q-learning. So Q-learning is, like we said, is one of those methods which is model-free, and the general idea is, remember, at any given point in time, the thing you want to maximize is this return, right? So, and we have this notion of value. At some state, there's at any given state, there's the value of that state, which is the expected return from that state if you follow some policy. So if we knew that those values, then getting a policy would be much easier. So that is this target. That is the value you're trying to estimate. So the idea is you make some estimate, so that you try to estimate something, and then the environment tells you, and then you compute it, and then you have your error term in that case. Should have been an equation there. And then, just like in gradient descent, so this looks very familiar to gradient descent, right? So you have a notion of a step size, and this is where you are. So this you can do this with gradient descent, that's the idea. So this class of method is called temporal difference. So there's a difference here, then you do a step, and then you keep improving progressively. So Q-learning uses this intuition with a few other tricks, and actually most reinforcement learning algorithms somehow use this kind of idea. You have a question? Sorry? Yeah, so the overall goal is you want to maximize the total energy generated, right? Assuming you already used the correct policy. But first we want to find the correct policy, and to get there, we want to estimate what is the value of those states. So, the value, remember, is the average return, so in which case the average energy from any given point, any given state up to the end. So in our case, if we say this thing is episodic, so it's which resets on a day basis, for example. So a state could be sometime, I don't know, during the noon, you have some particular state. And in that state, for example, the optimal thing to do would be to tilt it a little bit to the left, because that will generate a certain amount of energy. So that is the value of that state. So this is what we're trying to estimate, because once we know those things, then it's easy to extract the policy for all the states. Any other question? Before I show so this actually works. So I said we generate synthetic or simulated cloud cover. So in a practical sense, you'd put a camera to measure this. But in the simulated case, we use generate. So this is a sky without cloud cover. So that you can imagine that is the sun. And then we generate some cloud cover using a Gaussian. So this one we're using 16 by 16 images to simulate this. And then using this simulated data, we can run the experiment. So this green one, so this is day 1, day 2, like that. This is the energy generated, and we keep increasing. And like I said, the idea is you need to beat doing nothing. And so here I'm comparing it better than doing nothing, because physics people already know where the sun is and where the earth is. So you can imagine there's an intermediate between doing nothing and using a reinforcement learning, which is, if you already know where the sun is and where the earth is, we can just compute where that line of sight and then turn the thing, right, without doing any learning. So that is called solar tracking. So the people have developed this. So there's no machine learning there. It's just at any given point in time, we know where the sun is, we know where the earth is, so we can find out how much we need to orient our things. So always point it to the sun. But the problem with that is it doesn't take into account the cloud cover. So you see that if you use reinforcement learning, we're able to do slightly better than that using a very basic RL algorithm. And I mean, you can go crazy with this, and or you get real data. And I'm sure if you were to implement this, you can make much more efficient things. So, any question on this? So, who is going to try this? All you need is a panel and some Arduino and some camera. So that's a taste of reinforcement learning. So here I'm just gonna walk over a few things to look into. Like now we've seen that in this solar panel optimization problem, you can use reinforcement learning, but that doesn't mean you should always use reinforcement learning. How do you know if it's even a good idea to use reinforcement learning for your problem? So because sometimes you don't even need machine learning, like we said. You see here, somebody who is just using the laws of physics, just pointing the thing at the sun, is also doing better than nothing, and maybe you're satisfied with that, depending on your task. So if you're going to use reinforcement learning, I would emphasize a lot in this kind of recipe. So I really emphasize on the formulation, like really make sure you understand the clear notion of what is the state, what is the actions, what are the possible things you can do, because a mistake in the formulation here can lead you to muddy waters. You can end up with a million states, and then your algorithm takes days to converge, and even after those many days, you usually get a terrible result. So before you dive in and just trying reinforcement learning, really kind of do a mental walkthrough to see what do you expect to gain from this, because the algorithms are very computationally intensive and the investment is a lot before you get into it. And this today, if you Google reinforcement learning, there's a lot of the popular algorithms are all very complex, use a combination of deep networks and whatnot. It will take you days to implement it. It will need a gigantic computer. So before you get into that, try the simplest thing, just like in supervised learning. Try k-nearest neighbors before you do anything complicated. And the last point is key. Sometimes you don't even need to do machine learning.